Application to inverse trigonometric integrands. Okay, so let's move on to applying what we've learned about substitution to a new type of problem. As you recall from the previous sections, we've been mastering the technique of substitution to simplify integrals involving algebraic expressions, things like polynomials and rational functions. Now, we're going to see that this same powerful method works beautifully even when we encounter more complex functions, specifically what we call transcendental functions. Think of transcendental functions as functions that go beyond simple polynomials, things like trigonometric functions, exponential functions, and, importantly for us right now, inverse trigonometric functions. The core idea remains the same. We aim to simplify the integral by changing variables. Now, the key to successfully using substitution with these types of functions is being able to spot a relationship between a function itself and its derivative within the integral. This is crucial. Let's focus specifically on inverse trigonometric functions appearing inside an integral, what we call the integrand. When you see something like inverse tangent of x or arcsin of x inside an integral, your first instinct should be to check if the derivative of that inverse trigonometric function is also present in the integrand. For example, let's consider the inverse tangent function. Written as arctangent of x, its derivative is 1 over 1 plus x squared. So, if you see both arctangent of x and 1 over 1 plus x squared within the same integral, that's a strong signal that substitution is going to be a very efficient way to solve the problem. It sets up a perfect scenario for simplifying the integral and finding a solution. We'll see exactly how this works in the following slides with a step-by-step example. Conceptual approach. This slide explains why we're doing what we're doing. The overall goal here is to take what might initially look like a complicated integral, one involving inverse trigonometric functions, and simplify it down to something we can easily solve using the power rule for integration. You'll recall the power rule states that the integral of x to the power of n is x to the power of n plus 1 divided by n plus 1. We want to get to that point. We achieve this simplification through a three-step process. First, we need to identify the function within the integral whose derivative is also present. As we discussed earlier, recognizing this pairing is key. Second, once we've identified that function, we substitute it with a new variable. We often use t for convenience, but you could use any variable you like. This is where we're essentially changing our perspective on the integral. And finally, and this is crucially important, we need to update the limits of integration. Because we've changed our variable from, say, x to t, the limits need to reflect the corresponding values of t at the original limits of x. We'll see this in action on the next few slides with a concrete example. Don't skip this step, as it's a common source of errors. Okay, so let's move on to slide 2, where we discuss the conceptual approach to solving these types of integrals. Now, remember from the previous slide, we identified that substitution is a powerful tool when we see an inverse trigonometric function and its derivative within the integral. Keep in mind, we're setting ourselves up for a much easier integration. By doing these three things, we're transforming a potentially difficult problem into something straightforward that we can solve using basic integration techniques. Step-by-step example. Okay, so let's move on to a concrete example, as promised. This slide begins to walk us through solving a definite integral step-by-step. We're asked to evaluate the definite integral, which is represented by the capital letter I, and it's equal to the integral from 0 to 1 of the function arctan of x divided by 1 plus x squared with respect to x. Remember, arctan of x is just another way of writing the inverse tangent of x. Now let's begin with step 1, identifying the substitution. As we discussed on the previous slides, the key to using substitution effectively is recognizing a function and its derivative within the integrand, the part of the integral we're integrating. If you look closely at the integrand, you'll notice we have arctan of x, and importantly, we also have its derivative, which is 1 divided by 1 plus x squared. Remember from our earlier discussion, the derivative of arctan of x is 1 divided by 1 plus x squared. Because we have both the function and its derivative present, this is a perfect candidate for substitution. So, to simplify things, we're going to make a substitution. We'll let t be equal to arctan of x. This is our new variable, and we'll express the entire integral in terms of t. This substitution is the foundation for simplifying the integral, and in the following steps, we'll see how this transforms the problem into something much easier to solve. We'll then be able to use the simple power rule for integration that we're all familiar with. Step-by-step example, continued. Okay, so we've established our substitution. Remembering from the previous slides, we've set t equal to inverse tangent of x now. Let's move on to step 2, finding the differential. What a differential essentially does is tell us how a small change in x relates to a small change in t. To find it, we need to differentiate t with respect to x. So we calculate dt by dx, which is the derivative of t with respect to x as we discussed earlier. The derivative of inverse tangent of x is 1 over 1 plus x squared. So, dt by dx equals 1 over 1 plus x squared. Now, to make this useful for our integration, we rewrite this equation. We multiply both end sides by dx to get dt equals 1 over 1 plus x squared multiplied by dx. This dt is what we'll substitute into our integral, replacing the part involving x and dx. Now let's move on to step 3, transforming the limits of integration. This is crucial. Remember, we're changing our variable of integration from x to t, so our limits need to reflect that change. If we don't update the limits, our answer will be incorrect. Let's start with the lower limit. When x equals 0, we need to find the corresponding value of t. So we calculate inverse tangent of 0. The inverse tangent of 0 is 0. Therefore, when x is 0, t is 0. Now, let's do the same for the upper limit. When x equals 1, we calculate inverse tangent of 1. The inverse tangent of 1 is pi over 4. So, when x is 1, t is pi over 4. So, to summarize, our new limits of integration will be from 0 to pi over 4, corresponding to the values of t when x is 0 and 1 respectively. This sets us up perfectly for the next step, where we'll actually perform the substitution and rewrite the integral in terms of t. Step-by-step example, continued. Now step 4, substitute and rewrite the integral. This is where we actually make the change. We previously defined t as the tan inverse of x, so everywhere we see tan inverse of x in the integral, we replace it with t. Also, we found that dt is equal to 1 over 1 plus x squared dx. This means we can replace 1 over 1 plus x squared dx with simply dt. Crucially, we also need to update our limits of integration. We're changing our variable from x to t, so the limits need to reflect this. We already calculated these in the previous step. When x is 0, t is the tan inverse of 0, which is 0. And when x is 1, t is the tan inverse of 1, which is pi over 4. Therefore, our integral now transforms into a much simpler form. I equals integral from 0 to pi over 4 of t dt. Notice how much cleaner that looks. We've successfully converted our original integral into one involving just t, which we can handle much more easily. Now, step 5, evaluate the simplified integral. We're going to use the power rule for integration. The power rule states that the integral of t to the power of n dt is equal to t to the power of n plus 1 divided by n plus 1. In our case, n is 1, so the integral of t dt is t squared divided by 2. We write this as an indefinite integral first, giving us I equals t squared divided by 2, with the limits of integration from 0 to pi over 4. This is represented with square brackets as t squared divided by 2, evaluated from 0 to pi over 4. We're now in a position to apply those limits in the next step, and will be very close to our final answer. Remember, the goal is always to simplify the integral to a point where we can easily evaluate it, and we've done just that here. Okay, let's move on to slide 5. As we've established in the previous slides, we're tackling this definite integral. I equals integral from 0 to 1 of tan inverse of x divided by 1 plus x squared dx. Remember, we identified that the tan inverse of x was a good candidate for substitution because its derivative, 1 over 1 plus x squared was also present in the integrand. Step-by-step example continued. Okay, so we've reached the final step in evaluating our definite integral. As we discussed in the previous slides, after performing the substitution and simplifying the integral, we need to apply the new limits of integration. Now, remember our antiderivative. We found that the integral of t with respect to t is 1/2 t squared. So, we have 1/2 t squared evaluated from our lower limit to our upper limit. Let's apply those limits. Our upper limit was pi over 4, and our lower limit was 0. So, we substitute t equals pi over 4 into our antiderivative, and then subtract the value of the antiderivative when t equals 0. This gives us 1/2 multiplied by the quantity pi over 4 squared minus 0 squared. Remember that 0 squared is simply 0, so that term disappears. Now let's simplify pi over 4 squared. That's pi squared over 16, so we have 1/2 multiplied by pi squared over 16. Finally, multiplying 1/2 by pi squared over 16, we get pi squared over 32. Therefore, the definite integral from 0 to 1 of tan inverse of x divided by 1 plus x squared dx is equal to pi squared over 32. And that concludes our example. As we saw, by recognizing the pattern and applying substitution, we were able to transform a seemingly complex integral into a straightforward power rule integration. Remember to always double-check your limits and be mindful of the derivatives of inverse trigonometric functions, as highlighted in the upcoming slide on common mistakes. Real-world analogy. Think of this entire process, this substitution technique, as changing the lens of a camera. Now, imagine you're trying to take a picture, but the image is blurry. That blurry image represents our original integral, the one written in terms of x. It's complex and difficult to work with directly. By substituting, letting t equal inverse tangent of x, we're essentially switching to a different lens on the camera. This new lens brings the problem into sharp focus. What was once a complicated trigonometric fraction, involving inverse tangent of x divided by 1 plus x squared, transforms into something much simpler, just a linear variable, t. Remember, we successfully rewrote the integral entirely in terms of t, and that made the integration process straightforward, allowing us to use the basic power rule. So, once we've done the calculation in this clear view, with the problem nicely focused, we have our final answer. It's like finally getting that crisp, clear photograph after adjusting the camera lens. Okay, let's move on to a way to think about what we've been doing. This slide uses a real-world analogy to help solidify the concept. This analogy should help you remember why we do these substitutions. It's about simplifying the problem to make it solvable. And as we move on to the next slide, we'll discuss some common pitfalls to avoid so you can consistently get that clear picture with your integration problems. Common mistakes to avoid. First, and this is extremely common, is forgetting to change the limits of integration. Remember, when we performed the substitution, we weren't just changing the form of the integral, we were changing the variable of integration. So, if you substitute and get everything in terms of t, you must also express the original limits, in our previous example, 0 and 1, in terms of t. If you don't, you're essentially integrating with respect to x, while everything else is in t, and that will give you the wrong answer. Always update those limits immediately after defining your substitution. It's a crucial step. Next, let's talk about confusion between tangent of x and inverse tangent of x. This is a classic source of errors. It's vital to remember that we were looking for the derivative of the inverse trigonometric function. Inverse tangent of x, the derivative of the regular tangent function, tangent of x, is secant squared of x. However, the derivative of inverse tangent of x, which is what we needed for our substitution, is 1 over 1 plus x squared. Make sure you're using the correct derivative. Finally, incorrect limit values. This is about knowing your inverse trigonometric functions. For example, you need to recall that the inverse tangent of 1 is equal to pi over 4, not simply 1. It's easy to get tripped up on the actual values these functions return, so double-check those, especially when dealing with definite integrals. Knowing these standard values will save you time and prevent errors. Okay, let's move on to slide 8, where we discuss some common mistakes students often make when tackling these types of integration problems. Paying attention to these will save you a lot of frustration. So, keep these 3 points in mind as you practice, and you'll be well on your way to mastering integration with inverse trigonometric functions. On the next slide, we'll summarize the key takeaways from this entire section. Key takeaways. Okay, let's wrap up our discussion on integrating inverse trigonometric functions with these key takeaways. First, and this is really important for spotting these problems, is pattern recognition. You should train your eye to immediately look for specific pairings within the integral. Specifically, if you see the inverse tangent function, arctangent of x, alongside 1 over 1 plus x squared in the integrand, that's a huge clue that substitution is likely the way to go. Similarly, if you spot the inverse sine function, arcsine of x, paired with 1 over the square root of 1 minus x squared, that's another strong indicator. Recognizing these pairs will save you a lot of time and effort. Next, let's talk about efficiency. Remember how we changed the limits of integration when we substituted? That is, we found the new limits in terms of our new variable t. Well, doing that, changing the limits of integration as we did in our example, is generally faster than waiting until the very end to substitute back in terms of x. It avoids an extra step and potential for errors. So, get into the habit of updating those limits right away. Finally, and this is the big picture, simplification is the name of the game. The whole point of using substitution with these inverse trigonometric functions is to transform what initially looks like a complicated integral into something much simpler. We want to reduce the integrand. That's the function we're integrating down to a basic algebraic form, like just t or t squared. Once it's in that form, we can easily integrate it using the power rule, which you're already familiar with. So, keep these 3 points in mind as you practice, and you'll become much more confident in tackling integrals involving inverse trigonometric functions. Are there any questions about these key takeaways before we move on?